Kerry Emanuel is the Cecil and Ida Green Professor of Atmospheric Science in the Department of Earth, Atmospheric and Planetary Sciences at MIT. After completing his doctorate at MIT in 1978, he joined the faculty of the Atmospheric Sciences Department of UCLA, where he remained for 3 years, with a brief hiatus filming tornadoes in Oklahoma and Texas. So I really think there probably are some very good stories there. And then returning to MIT in 1981. He is the co-founder of the MIT Lorenz Center, a climate think tank, which fosters creative approaches to learning how climate works. Professor Emanuel's research is focused on tropical meteorology and the physics of hurricane development. His work has explored the role of climate change on hurricane activity. He is the author or co-author of over 200 peer-reviewed scientific papers and 3 books, including Divine Wind, The History and Science of Hurricanes, published by Oxford University Press, and What We Know About Climate Change, published by the MIT Press. He is the 2020 recipient of the BBVA Foundation Frontiers of Knowledge Award in Climate Change and a member of the National Academy of Science.
Wow.
All right. So, Dr. Emanuel, when you're ready to go, we are waiting to hear you speak.
Wonderful. Well, thank you for your very generous introduction, and it's nice to kind of meet all of you. I wish we could be in person, but we're all coping with this. And my program for today is to try to run you through a little tutorial on climate science. And I'm going to talk about the science itself. I'm going to phrase the global warming problem as a problem of risk, and also talk about opportunities. Where there's risk, there's opportunity, and I think that's a very important point to make. But I want to say before I begin that those of us who do climate science do it for the same reason all of you do what you do. We love it. We would be doing climate science if we didn't have a climate problem. We're portrayed in the press as solely devoted to trying to tackle the global warming problem, but that's far from the case. And I think it's important to keep in mind that we're a science just like any other science, and scientists like other science. And we're kind of the same motivations and hopefully the same joy. So the program for this morning is going to run you through a little history of Earth's climate and climate science, and talk a little bit about the evidence that we're doing some climate, and then phrase the global warming problem as a problem of risk. We're all familiar with dealing with risks of various different kinds. Talk about it and frame it this way. And then, very importantly, talk about technological solutions to these problems. I won't talk about political solutions because I don't have any idea how to do that. So let's begin at the beginning. So let's talk about how the Earth's climate has varied, because it's varied on all kinds of different time scales over 400 billion 4 billion year history. So a very high frequency fluctuation, at least by the standards of the age of the Earth, is the great advances and retreats of land ice sheets, particularly in the Northern Hemisphere. What I'm showing you in this graph is a record from ice cores in Greenland at the top and in Antarctica in the middle, going back 450,000 years. So the chart begins at the left, 450,000 years ago, and runs to today on the right. And if you look at the blue curve on the top, you see these ups and downs. So this is a reconstruction of temperature, basically, in Greenland. And how we do that is a really fascinating story, which I wish I had time to tell you, but it has to do with measuring the 2 isotopes of oxygen in the water of the ice cores, and tells us the temperature. The green is exactly the same thing, but from an ice core in Antarctica. And when you look at these two, what you see are these fluctuations where the temperature is relatively low, and then it spikes upward, and then it goes back down. And we're in a relatively warm period now at the extreme right. is called an interglacial, and we've had quite a few before. Over the last 3 million years, there's been about 10 of these glacial episodes. You can see Antarctica and Greenland are very well correlated. The blue and green curves are pretty similar. The bottom curve in the red is a completely different thing. It's again, looking at isotopic ratios, but in deep sea cores. And very remarkably, they tell us something about the total volume of ice on the planet. That curve has been flipped upside down so that low ice volume is on the top and high ice volume at the bottom. And you can see that when it's warm, there's not much ice, and when it's cold, there's a lot of ice. The fact that these very independent records all line up gives us quite a bit of confidence. There's lots of other evidence that influence cycles. And here is the last construction of the Lorenz ice sheet over North America at the peak of the last glacial cycle about 20,000 years ago. 20,000 sounds like a long time, but human beings as a species have been around for a long time, although not civilization. But if you're in New York or Boston or up in the northern plain states or northern Midwest, you would have been under a mile or two of ice 20,000 years ago. So that's a lot of climate. This graph shows what happened to sea level as ice began to melt at the beginning and the termination of the last glacial episode. So this graph runs from 24,000 years ago to today at the right. And at sea level relative today to today's in meters, so zeros at the top. 22,000 years ago, at the last glacial maximum, was 130 meters, 120, 130 meters lower. That's 400 feet. So if you could have crawled out in Boston from underneath that big ice sheet, you could have walked directly from Boston Provincetown without getting your feet wet. There was no water in Cape Cod Bay, and it's a lot of sea level. Now you notice that sea level stabilized starting about 7,000 years, and anthropologists don't think it's a coincidence that when we entered this remarkably stable period of climate called the Holocene, it's about the time human civilization developed. We stopped being completely nomadic. We started herding cattle and so on. So there's a link, I think, between climate stability and civilization. And one of the points I want to make is that in the last 7,000 years, human civilization has grown spectacularly, and human infrastructure is extremely, exquisitely finely adapted to the climate, to the unusually stable climate we've enjoyed for the last 7,000 years. If any change, whether it's up or down, doesn't really matter. It's going to be up. Now, the remarkable thing is that we know almost certainly why the Earth went in and out of these glacial episodes. And the solution was proposed actually back in the 19th century, but more recently revived by this Serbian mathematician, Milankovic, lived from 1879 to 1958. And he was aware, as astronomers had been for a long time, that the Earth's orbit around the sun in the first place isn't a circle, it's an ellipse, like most planetary orbits, and that the degree of ellipticity, the departure from circularity itself, varies on about 100,000 year time scale. Moreover, the Earth's rotation axis is tilted with respect to the plane at which the Earth orbits. Everybody knows that, that's why we have seasons. But the degree of tilt, which is of course dictating the degree of seasonality, wobbles on a period of about 41,000 years. And finally, the direction that the axis is pointing also sort of spins around or precesses, just like a child's top on the floor, it sort of wobbles around. And all of these three change not so much the total amount of sunlight that's intercepted by the Earth, but the distribution of that sunlight with latitude. And Milankovic said, you know, he thought that ice ages started when the amount of sun sunlight intercepted at very high latitudes up in the Arctic got too low. And of course, back in his time, everybody thought he was a crackpot, but we now know that this proposal was spot on. And how do we know that? From records like this. So here's another graph, yet another graph going from this time 1 million years ago at the left, or 1,000 years. This graph is in thousands of years, up to the present on the right. And it's showing two completely different quantities. The amount of sunlight coming into the high latitude Arctic, that's in red. And the blue is literally the time rate of change of the ratio of two isotopes of oxygen in deep sea sediments. And you recall from a few slides ago, this is a measure of ice volume on the planet. And so what this shows is that when there's a lot of sunlight, the ice volume is going down. That ratio is actually going up, but the ice volume is going down. And vice versa. They're very well correlated. And this basically is a proof of the Milankovitch hypothesis. So one of the great accomplishments of climate science, I would say, in the last few decades is, first of all, recognizing that there were ice ages, that goes back 100 years, but figuring out why they happened. And that this is not even new. I mean, Milankovitch did this more than 100 years ago. So we have some feathers in our cap as a profession. We understand why there were ice ages. Now, another really important thing we haven't talked about is fluctuations in the composition of the atmosphere, which affect climate through the greenhouse effect. Now, the greenhouse effect, everybody's heard that expression. I just wanted to say a little bit about what it is, because it actually doesn't have a whole lot to do with greenhouses. We're kind of stuck with that term. But it turns out that there are certain gases in the atmosphere which trap radiation. And way back in the middle of the 19th century, this dour-looking Irish physicist, John Tyndall, figured out which gases in the atmosphere are greenhouse gases. And greenhouse gases are gases that absorb and emit infrared radiation. And it had been known before John Tyndall's time the atmosphere did that, but nobody quite knew what parts of the atmosphere, what constituents of the atmosphere did it. It's a chemistry problem in a way. And so he built this apparatus, which you see a nice drawing of. And if you want to see the real thing, it's on display at the British Museum next time you go to London. Next time they let us go to London. And you see there's this long tube, and he could fill that with gases of his choosing. And then he'd shine a light through it, various different wavelengths, and absorb and measure how much of that light was absorbed as it went through. And thereby, he was the first to quantify the greenhouse effect of the atmosphere. Now, what is the greenhouse effect? Well, let's suppose we lived on an Earth-like planet, just like Earth, except there weren't any greenhouse gases. The atmosphere was there, but it didn't happen to have any greenhouse gases. It would be very simple to calculate its surface temperature if you knew how much sunlight is reflected. So you have sun coming in, and some of it's reflected, and then the Earth begins to heat up. Now every object that has any temperature emits radiation, and the Earth's surface emits, because of its temperature, in the infrared band. And so the Earth will heat up until it starts emitting as much infrared radiation as solar radiation absorbed. It's very, very simple to calculate what temperature is necessary for the surface to be at to balance the sunlight coming in. And it's minus 18 degrees centigrade. That is, if that was actually the situation, the whole planet would be frozen. In fact, it'd be much colder than that, because if it's frozen, all the ice would be reflecting most of the sunlight. So that was understood by Jean-Baptiste Fourier at the end of the 18th century. This, what I'm showing you here. So they knew even back then there was something else going on. Now, if you have greenhouse gases, what they do is they absorb some of the infrared radiation coming up. Now, if they do that, of course, they're going to get hotter and hotter, but they're also emitting infrared radiation. So they have to get hot enough to emit infrared radiation, enough infrared radiation to balance what they're absorbing. But they emit it both up and down. And so if you're at the surface, you're getting radiation not just in the form of sunlight, but you're getting infrared radiation coming back down at you from the atmosphere, and I should say also from clouds in the atmosphere. And so the surface of the Earth has to get warm enough to emit enough radiation, not just to balance the sunlight, but to balance the back radiation coming from the atmosphere. Now, the remarkable, and this is the greenhouse effect. It's the fact that the Earth has to balance not just sunlight, but this back radiation from the atmosphere and clouds, and it's radiating 24/7. And in fact, on average, we get twice as much radiation from the atmosphere and clouds as we do from the sun. That's how powerful our greenhouse effect is. And that makes a difference between a surface temperature of -18 degrees, which is about 0 Fahrenheit, and the observed mean surface temperature, which is closer to 15 degrees. So in a nutshell, that's the greenhouse effect. And Tyndall figured out which gases are doing it. And his results shocked him. And it shocked all the scientists of his day. Because the first thing he did is what all of us would do. We put in the most important constituents of the atmosphere, which are oxygen and nitrogen. And then the third one down the list is argon. They make up 99% of the atmosphere, and they didn't do anything. They didn't absorb any kind of radiation he sent through this apparatus. Of course, he thought there was something wrong and checked and checked and checked and checked. Nothing. So it was sort of surprising that where's the greenhouse effect? So he started putting in trace gases. And he started with water vapor, and then carbon dioxide, nitrous oxide. It turns out that these trace constituents, you meght notice that the molecules here are more complex molecules than oxygen and nitrogen, and that's key. Metric molecules of 2 atoms each, and because they're so symmetric, they can't really interact very well with radiation, but the more complex molecules, H2O, CO2, N2O, do, and they together make the lower atmosphere almost opaque to infrared radiation. Although they don't do very much absorption in the solar. A little bit, but it's mostly an infrared effect. And so these gases together make the difference between a surface temperature of 0 degrees Fahrenheit and 60 degrees Fahrenheit. So that was weird, you know, these gases aren't very plentiful. Here's a pie chart showing this. Nitrogen, 78%, oxygen, about 21%. Those are the blue slices. Argon is green. It doesn't do anything either, by the way. So all those greenhouse gases are in that tiny little sliver, which you can barely see. And most of that's water vapor. But it's even more weird than this, because the water vapor is the most important greenhouse gas, but it's in turn controlled by temperature. It's about 0.25% of the mass of the atmosphere, but it basically is controlled by temperature on a time scale of about 2 weeks. So it's responding to climate change and it's amplifying it. You make it warmer, there's more water vapor, it's a greenhouse gas that makes it warmer yet. It's a positive feedback mechanism, but it doesn't control climate on long time scales because it's just a responder. The things that are driving it are the long-lived greenhouse gases, most notably carbon dioxide, but also methane, nitrous oxide. And they comprise 0.04% of the mass of the atmosphere. And that's the rub. And that's why people find this very hard to believe that these tiny, tiny trace gases are controlling climate. And of course, the problem is the concentration of the most important of those long-lived gases has increased by almost 50% since the dawn of the Industrial Revolution. Now, of course, we all know that tiny bits of quantity can have large effects. If you were to ingest not too many molecules of arsenic, you'd be dead, right? Or you can go to a warehouse with an old-fashioned thermostat and a tiny little bead of mercury is controlling the temperature of that whole warehouse. So yes, little things can cause big, but when you have a situation like this, there's a strong suspicion that the concentration of those trace gases is strongly regulated by nature. Otherwise, things would spin out of control pretty easily. So The problem is that we basically are tampering with this natural thermostat. And we've had a big influence on them. And interestingly enough, that influence was predicted by a chemist. Svante Arrhenius is a Nobel Prize winning chemist. He lived from the middle of the 19th century till 1927, and he looks even more unhappy than John Tyndall. I don't know what it is about climate scientists that they look so miserable. Maybe they were setting a standard for the rest of us, I don't know. But he wrote back at the turn of the last century, actually, the first shot he took at it was in 1897, that if you were to double carbon dioxide, he was worried about that because he was sort of living during the beginning of the Industrial Revolution, and sort of calculated that maybe if we kept burning fossil fuels, carbon dioxide would go up, and did some calculations to show that if you doubled the amount of carbon dioxide, you'd raise the surface temperature by about 4 degrees. Now, this was a calculation obviously done completely by hand based on infrared measurements of the moon. Very, very interesting science. And the modern estimate of the response of the Earth to doubling carbon dioxide is between 2 and 4.5 degrees. So think about that. Basically, this chemist from the end of the 19th century got this right well over 100 years ago. And yeah, maybe the central estimates are a little bit lower than that, but basically in the right ballpark. All that modern science has been able to do is put error bars on that. What happened with Arrhenius? I mean, he made a prediction. Did it turn out? Well, you can judge for yourself. So the blue curve is a measure of the concentration of carbon dioxide. It's actually the natural log of the concentration because the radiative effects of carbon dioxide scale logarithmically with that. That's the blue curve. That's measured before 1958 from ice core, bubbles trapped in ice cores, and since 1958 directly measured by a big observatory on Mauna Loa in Hawaii. And yeah, it's been going up a lot. As I said, about 50% over this period. And the red curve is a global mean surface temperature, which has been measured pretty well through most of this period. And it squiggles, it goes up and down, there's natural variability. Volcanoes influence surface temperature for 2 or 3 years. There are man-made aerosols. By and large, I would say, looking at this, that Arrhenius's prediction, the blue line, matches what actually happened pretty well. So I wanted to get across to you that there's nothing particularly new about this concern about greenhouse gases and climate. As I mentioned to you, by analyzing bubbles of atmosphere trapped in ice cores, and we can date the ice cores pretty well now, we can see how carbon dioxide has varied before we started measuring it. And this is based on ice cores. By the way, the carbon dioxide concentration is globally pretty uniform, because they're such long-lived gases, they get mixed up by atmospheric turbulence. So if you measure at one place, you basically measured it everywhere. So you can see that starting 1,000 years ago at the left, the concentration's been about 280 parts per million, pretty stable up through the dawn of the industrial age, and then rocketing upwards. And in fact, you know, the graph ends at 400 over on the right, and we're at 410 at the moment and climbing. So that spike is something we did. There's no doubt about it. It's not just looking at this graph that tells us this, but looking at the particular isotopic composition of the carbon dioxide that tells us that it's man-made. This is a record, a proxy record of air temperature in the high latitude Arctic, based upon, again, isotopic and other approaches going back 2,000 years. So it's 2,000 years ago on the left. You can see that the temperature in the Arctic was actually declining slowly. And this is in accord with the Milankovitch forcing. We're on a down curve on that. But then beginning around 1800, it just really took off. And the red curve is actual measurements. And we did that, okay? There's no doubt in the scientific community that this is the case. Now, of course, you may have noticed that up till now, I haven't even mentioned climate models, but we do have those. if you listen to the media, pay attention to what's going on, read newspapers, you might come away with the impression that everything we know about climate comes from models, and that's really not the case. They're one of many, many tools we use. But climate models are sort of consistent with this. So what you see on this graph, going back 100 years, a little more than 100 years, is an attempt to replicate with climate models the evolution of the Earth's temperature over this 100-year period. And the observations of global mean temperature are the black curve relative to the value in 1880 or something like that. The red curve is the mean of a whole set of climate models, and the red shading is the dispersion of the climate models around that mean. And you can see that they do a pretty good job. And they include in them man-made forcings, the greenhouse gases, and also aerosols, which reflect sunlight, which is a byproduct of biomass burning, fossil fuel combustion, and so forth. The blue curve is going back and doing the same experiment over with those models, and but omitting the anthropogenic forcings. And you can see that after about 1960, there's no way you can get close to what happened unless you put in the anthropogenic components. So I want to sort of switch to the discussion now, because I really would like to leave a lot of time for questions to the future. I've sort of given you some very, very elementary idea of what we know about climate, but there's a lot more to it than that. Let's talk about the future. And the problem, of course, is that, you know, prediction is very difficult, especially when it concerns the future. That's a quotation from Niels Bohr, the Danish physicist. There's uncertainty. Nobody in the scientific community denies that there's still a lot of uncertainty in this whole science, and it prevents us from making very confident predictions. That doesn't mean we can't make predictions that have value. Scientifically, the sources of the uncertainty, first of all, clouds. Clouds are very hard to model, it turns out. They are responsible for most of the reflection of sunlight back to space. About 30%, pardon me, of incoming sunlight is reflected. And most of this is done by clouds. But clouds are also greenhouse agents. They absorb upwelling infrared, emit some of it back down to the surface. So they're working both sides of the climate stream. Water vapor, I mentioned, is a positive feedback. That's completely agreed, but exactly how much water vapor is added when you warm the atmosphere depends upon all kinds of interesting physical processes that's not perfectly well understood. The ocean's response, that's something that needs a lot of work too, and aerosols in the atmosphere. Now, when we get together and talk about projections of climate, we are completely open and honest about the degree of uncertainty. And this is perhaps the most important graph I'm going to show you here. It is a projection of the equilibrium response of our climate to doubling carbon dioxide. And it's not just one number, it's a whole probability curve that runs from about 1 degree on the left to 7 degrees on the right. And it's basically the vertical axis is probability. So the most probable outcome for doubling carbon dioxide is in the range of 2 to 3 degrees, or maybe 2 to 3.5 degrees C, okay? And there is about a 5% likelihood that it will be less than 1.8 degrees, and a 5% likelihood that it will be more than about 4.5 degrees. So there are these tails on the distribution. Now, the problem is that in any kind of risk problem, you have to worry about those tails because the cost of the climate change is very, very non-linearly dependent on how much there is. You know, if we have a degree and a half, there'll be changes to be sure, and we'll have to adapt to be sure, but it probably won't be catastrophic. If we have 5 degrees, according to everyone who's looked at it, it will be catastrophic. And there's no point in softening that language. It would be catastrophic, not for the Earth, but for civilization. But the most probable outcome for doubling is somewhere in between those. And this is the hard part of the problem. We're dealing with how do you cope with an uncertain outcome when the tail of that distribution is very dangerous, and the middle of it is already moderately dangerous. Pardon me for just a second. Okay, so the problem is that unless we do something about it, we're on track to do a lot more than doubling carbon dioxide. If India and Africa develop their economies, and I think we all devoutly hope they will alleviate their poverty and bad living conditions. If that happens in the century, you're going to triple carbon dioxide by the end of the century. This is just a bunch of projections of carbon dioxide concentration starting around 1960. And the blue dashed horizontal line is the doubling, is the value of carbon dioxide that doubles it from pre-industrial time. You see most of these curves go beyond that. So doubling is a fairly conservative thing if you're interested in what's happening 80 years from now. The problem is, and this is a chemistry problem, and this graph was given to me by my chemist colleague, Susan Solomon, is that carbon dioxide's residence time or lifetime in the atmosphere is very, very long. And that's illustrated by the graph at the top. So this is, again, a graph in time starting in the year 1800 and projected all the way out to the year 3000. And it is a bunch of hypotheticals. It shows carbon dioxide increasing according to what the economists tell us is likely on the left. But the experiments we do is say, let's just shut it off when it reaches various different contributions. So let's do an experiment where we shut it off when it's 450 parts per million, 550, all the way up to about 1200. And we're just going to instantaneously shut off all emissions and then calculate what actually happens to the carbon dioxide content. And what you can see is that initially it falls pretty quickly. Over a period of 100 years or so, it goes quite far down, but then it goes to a different time scale, which is dictated, it turns out, by how rapidly you can start to saturate the deep ocean with carbon dioxide. And it takes thousands and thousands and thousands of years for it to relax back to pre-industrial values. So to some good approximation, it's going to be whatever value of the carbon dioxide we have, subtract 20% or so, we're going to be stuck with it for a long time. At the bottom, we have the corresponding global mean temperature that corresponds to that carbon dioxide content. That's very interesting because you notice that it's almost flat. From the time you stop emissions, basically you're stuck with that temperature for 5,000 or 6,000 years. Why is that? Why doesn't it go down? Because there's a compensation that the ocean, the deep ocean, has a very long response time. You're storing up heat and releasing it, and that sort of compensates for the reduction of carbon dioxide. So this is the problem. If we're going to do something about CO2, boy, we have to act fast. All right, that's just dictated by chemistry. The only way around that is if we can figure out economically how to pull CO2 out of the atmosphere. We can do that artificially. We can accelerate this decline back to normalcy. What exactly, I mean, why should we care about the global temperature? I mean, how does it really affect us? One obvious way is through sea level. Sea level is increasing now because as you warm water, it's not completely compressible, it expands. And because land ice, particularly Greenland and Antarctica, is beginning to melt, and that, of course, increases the sea level. The thing that worries most of us, and this is a very simple piece of climate physics, is if you make the climate warmer, you increase hydrological extremes, both drought and flood. You get about as much rain as you used to get, but it's much more concentrated in time with much longer intervals between events. You have, this is something I personally work on, you have an increasing incidence of high category hurricanes and associated storm surges and freshwater flooding. You get more heat stress and other health risks. And the thing that keeps me awake and most of the Pentagon awake at night is that as you increase food and water shortages, you have immigration pressures, and that often leads to armed conflict in a nuclear armed world. That's the really dangerous scenario. But there are also benefits to warming the climate. Some increase in plant productivity is a direct result of more carbon dioxide in the atmosphere. Of course, you expect to see a reduction in health problems that are related to cold weather. But if you sum it all up, this goes back to my earlier point, we're so beautifully adapted to the climate of the last 7,000 years. Any change, doesn't matter whether it's going up or going down, is a negative. So we have to readapt, as we will. And the Intergovernmental Panel on Climate Change, IPCC, says that if you put everything together, there's a lot of net damages that we could expect from this change. This is sea level. Could I just ask, am I still with you? Because I'm hearing weird beeping. Somebody want to respond to me?
Yes, for me.
Okay, that's all I need to know.
Hi, Dr. Emanuel.
Yeah, you're still coming through loud and clear.
Okay, thank you. Thanks very much. Okay, so this is a record of sea level relative to its value in the year 2000 from proxy records and tide gauge. Projection of sea level going forward. And you can see, again, a lot of uncertainty there between 1 and 4 feet of sea level rise. And so it's, you know, that's disruptive. There are a lot of seaports, a lot of us live close to sea level. Heat, the problem there is you get more heat waves. This is just a projection of global mean temperature, again, going forward. These spikes represent heat waves, but up to a point, we adapt pretty well to heat. If it gets hot, over a long period of time, we either live in cooler places or we get air conditioning if we afford it, and so forth.
Hi, Dr. Emanuel. I'm sorry to interrupt you for a second.
Yes.
This is Chris Koutros. When you change the slides, I think it's having a lot of demand on your data connection. And so you get a little garbled when the slides change.
Okay. All right. I will try to pause just after I change the slide. That's interesting that should happen in the first place, but yeah. Okay, so the point here is that you expect more heat waves, but we do adapt after a while as a species to heat up to a biological limit, which is called the wet bulb temperature. If the average wet bulb temperature is more than about 37 degrees C, we can't survive. As I mentioned to you before, the big problem is hydrological extremes. So rainfall intensity, that is how hard it rains when it's raining, goes up very quickly with temperature. It doubles for every 10 degrees increase. And yet the overall global rainfall doesn't change much. And the only way to make that come out is if it's going to rain harder, it can't rain as often. And this translates in global climate models to places that are already wet get a bit wetter, places that are dry get drier. And so you expect an increasing incidence of both floods and drought. And this has big potential effects on food and water supplies. And it's considered by the Pentagon to be a major national security issue. Floods, you have more floods, you have more drought. And the Defense Department, I'll let you read that, is very concerned about this. It's one of their top national security issues. Carbon dioxide a lot of it ends up dissolved in the upper ocean. And this increases its acidity or lowers its pH. And this is measured changes in ocean pH over about 30 years. And you can see particularly in the North Atlantic and in the Southern Ocean, there's pretty hefty increases in acidity. The problem is that threatens marine life that depends on building shells, for example, both microorganisms and mollusks, things like that. Hurricanes are expected to get more intense. And this is a graph showing trends in observed hurricane intensity, percentage increases per decade as a function of how intense the storm is. So you can see weak storms aren't changing much, but there's a higher frequency of really intense storms. That was predicted 30 years ago, 33 years ago, and we're beginning to see it in the data now. And destruction goes up very quickly with wind speed. And I think I'll skip over this, but you can see this in the projections. Now let me just sort of finish up by saying this, and it sounds a little Machiavellian, but where there is risk, there is opportunity. And I think it's an important message for young people, because there are ways we can deal with that risk that you could look at as opportunities. The global annual energy market is about $7 trillion currently, about a third of US GDP. It's a huge market, and it's decarbonizing. This is not a philosophical or ideological point, it just is. People all over the world are demanding that we move away from carbon. And China, in particular, has moved to capture this energy market. It's the leading producer of wind turbines, solar panels, and so forth, and nuclear power plants, although it has competition in that from Russia and South Korea. We're not doing that, although I think some would argue that the US still has an edge in technical innovation, but so far we're not really in that game. And so while global warming is going to cost us something, the nations that lead in low carbon energy technology are probably going to come out ahead. What are the solutions and opportunities? Well, there's a lot of talk about renewables, and they have indeed really taken off, solar and wind, and they will continue to grow, but not indefinitely. Most energy experts say you can get up over very large regions, over whole power grids. I mean, obviously you can do 100% of your own house or your own town, but only about 40% sort of globally. And the problem is that once you get up to 40%, the fact that the sun doesn't always shine and the wind doesn't always blow means you have to be able to store energy. And current storage costs are about 10 times larger than they would need to be to make storage economically feasible. So you have to remember, when people talk about renewables, they're great up until you hit this limit of about 40%. If you have to supply 60% from fossil fuels, you're not going to solve the problem. Another promising technology, though, is carbon capture and sequestration. And this is mostly a chemistry problem again. We can do it. We know how to do it. We just don't know how to do it economically. It's 4 to 5 times too expensive to be feasible now. Now, who knows? But this is something you should mention to your students. This is where chemists could conceivably save the day for us. It's just too expensive now. It has to come down. Economists really tell me it's got to come down to $50 a ton to make it sort of feasible. And then we're not, at least in this country, incentivizing this very well. And then the other thing is nuclear fission and fusion. How do we actually go about catalyzing these solutions? Well, what 95% of the US economists or world economists say is to do something we've always done, is to price the negative externalities of carbon emissions. That is, you can't let an industry pass on the cost of its doing business to some other industry or to the population. We don't let the neighborhood mining operation dump their refuse in our backyards. They're not allowed to do that, but that's precisely what fossil fuels have been doing, is dumping all their waste in the atmosphere. Just charge them for it, okay? It incentivizes a migration away from that. It's a bedrock free market principle, very highly supported by economists. And if you did that today, coal, which is already on its way out, would vanish. the health externalities of coal are absolutely staggering. If you actually get into this, it's many, many millions of premature deaths around the world every year, as mostly from particulates emitted by coal. We should never be burning coal. And the markets wouldn't support it if coal had to pay for the health externalities, even forgetting about climate. And if you did this, it would be the markets rather than ideologies that would determine the best mix of solutions. But economists also say this is not enough. It's necessary, but it's not sufficient. We need to stimulate innovation, and smart governments are doing that. And ours, unfortunately, is not doing that very much. Now, I'm a big proponent of fission, not because I have any particular love of nuclear, but because we know from experience we can do it very fast. So these are graphs showing added electrical energy per person over an 11-year period, starting whenever that country started to develop its nuclear power. And you can say that Sweden, France, and Belgium really ramped it up fast. And Sweden and France today get very large percentages of their electricity from nuclear, and most of the rest of it from hydro. So neither country's energy sector, electricity sectors, are producing any carbon to speak of. And Germany at the bottom is red, and it actually ramped down its nuclear industry and tried to do it with wind and solar and just didn't get very far. And has the highest electricity prices in Western Europe today. This is one of the things, unfortunately, it's a myth that gets circulated around that nuclear is dangerous. We've had precisely one fatal nuclear accident, Chernobyl, that involved a power plant design from the old Soviet Union that nobody wanted and is not being built today. But even with that horrible accident, if you normalize by the amount of power generated by the source, it's the safest form of energy we've ever created, comparable to wind and solar, even safer than those. The really dangerous stuff is coal, with oil and gas not too far behind. Even hydro isn't very safe because there are occasional dam failures. That safety is not the issue. Waste is an issue, not safety. And just by having some nuclear power in the US, we prevent something like 13,000 annual premature deaths. But we can do a lot better, and we are. I mean, we're not proposing to build 1960s era reactors anymore. There's all kinds of new technology. I think I'm not going to go through this in detail, jump to the summary. The main points I wanted to try to get across today are that several aspects of climate science are pretty well established. The Earth's climate is strongly bounded. That is, it doesn't run away into catastrophic states naturally. We didn't get into an ice-covered planet, except very briefly. And we didn't have all our oceans evaporate and the temperature rocket up to 700 degrees C like happened with Venus. Venus is closer to the sun but absorbs less sunlight than the Earth because it's got a very bright surface. Yet it's much, much hotter, and that's because of all the greenhouse gas in it. Climate science is not new. A lot of very important discoveries date back more than 100 years. The Earth's greenhouse effect triples the amount of radiation absorbed by the surface, though it's regulated by great gases that comprise no more than 0.04% of the mass of the atmosphere. And the concentration of the most important of those long-lived gases is increased by roughly 50%. And beginning by the calculations of the Swedish chemist Arrhenius more than 100 years ago, predicting increases in response to doubling CO2 of around 3 degrees with some error bars. And they're also consistent with what we get out of models. But the long lifetime of CO2 limits the time frame in which we could curtail the risks unless we can figure out how to extract CO2 from the atmosphere. So the problem with renewables right now is you can't get up to about 40% of market penetration on a grid scale. You can do it locally, but you can't do it on a grid scale. Unless we can really have a revolution in storage. Fission can be ramped up very rapidly and economically, but in the United States, for a lot of reasons, we cannot do it economically. My proposition is we should start buying reactors, very reliable, very inexpensive reactors from South Korea, who are already exporting them all around the world. I think we should become a serious player in this transformation. It's a $7 trillion global energy market. And I'll leave it at that and be happy to answer questions. Thank you. I'm going to stop sharing my screen now. So I can see all of you.
There were a couple of questions that came up in the chat. One from Andrew. Andrew had a question about factoring in the life cycle. Andrew, did you want to chime in with that?
Yes, I'm trying to restart my video. It's getting hung up a little bit.
That's
but I don't really have anything to add unless the question isn't clear.
Okay. About factoring in the life cycle in terms of the safety of nuclear fission and the waste management piece.
Oh, yeah. So when we do these comparisons, and my energy colleagues at MIT are pretty good about that, yes, you have to factor in for all energy sources, all of the costs, the mining costs, the transportation costs, the waste disposal costs, and all of that. Nuclear is very uneconomical currently in the United States, mostly because we've lost the expertise. We haven't built them in a while. There's 1 or 2 plants being built. We've lost the manufacturing supply chain, and the regulations are really, really stiff. So I'm not very optimistic about that. Nobody can compete with frack gas. That includes solar, not without big subsidies. Nuclear doesn't get green power subsidies. Nuclear waste disposal is not considered by engineers to be a technical problem. We know how to do it. It's just a big political problem. Again, in the United States, Finland is taking European nuclear waste and burying it deep in very stable bedrock. It's not really a problem.
Catherine Fogarty had a question as well. Catherine, did you want to chime in? We've just got a couple of minutes before we have to head to our next session, so we're trying to get questions in.
About the 40% maximum that you can achieve with renewables, and I know, like on a small scale, if you have solar panels on your house, you can essentially send it back to the grid. Can that be done on a much larger scale so that you don't need to store vast amounts of energy?
That's a really good question. I'm talking to you from a house in Maine who has a barn with lots of solar panels, and we generate more in an average year than we use. But the problem is we're using the grid itself as a kind of battery. If you start getting up to 40%, then surrounding parts of the grid that are not on solar and wind have to have higher capacity to supply not just their own customers, but you when the sun isn't shining or the wind isn't blowing. And so they can do that, but you get up to about 40 or 50%, and then you can't do that anymore. You have to start storing it. So the grid, so you can do it locally. I mean, your own house can be like ours is 100%, but it just can't scale up. That's the problem.
Okay. Right. And then I think Tomas had a question about permafrost. Tomas, did you want to chime in?
Yeah, I was just wondering, I've been reading about this issue over the summer.
Your question in the chat was about concerned about the thawing of permafrost in Siberia, and it's adding methane to the atmosphere.
Okay. I do have the chat box up, but it's very hard for me to find the question you're talking about. So I'm just going to let you, Kristen, relate it to me.
Yes.
But the permafrost is a concern because there's a lot of methane locked up in it. And when it begins to melt, you release the methane. The question is, how much is there?
Mhm.
And the inventories I've seen, frankly, are all over the place. So I don't think there's a lot of certainty about that. It is a positive feedback. You know, one thing that keeps us awake at night is if we look at past natural climate change, we know the system is capable of very abrupt, sudden changes. Sometimes they're called tipping points, but we don't understand that. It may be that permafrost release of methane is responsible for some of those. This is why we don't like to tickle this tiger too much, because we don't know enough about it to know when it's going to wake up and do something unexpected.
All right. Well, it's been a fabulous talk, Dr. Emanuel. Thank you so much for meeting with us this morning. I'm sorry you weren't able to get to France as you had originally planned. But I don't think we're going to Europe for a while, any of us. We're going to move on to our next sessions. Anyone who wants to continue the discussion of Dr. Emanuel's keynote address, you can stay right in this meeting, and we're going to post a link for a discussion document. And anyone who wants to say, Dr. Emanuel, of course, you're welcome to stay for that. But we also understand that you have, other things to do and may not be able to stay. We very much appreciate you coming and talking with us today. And otherwise, we've got 3 other presentations that you can go to. Chris just posted the links to that. And so everyone's gonna make a choice now. You're either gonna stay here and discuss the keynote address further, or you're going to go to one of the other keynote addresses. And it's been great. Thank you very much. But I have another meeting to run.
Do you mind if I talk with you for a moment, Dr. Emanuel?
No, please go right ahead.
Okay. I understand that we have a way to sequester CO2 biologically. I can understand that. I can understand its impact on the ocean. I can understand, of course, phytoplankton, and its ability to absorb CO2. I did read an article at one point in time about methyl hydrate deposits in the ocean floors. And due to the increase of the temperature of the ocean, they can have rapid releases. Like I believe some off of Sweden, they found these craters. They couldn't figure out how they formed, and the thought was methyl hydrate. I know it could be a viable fuel source if we could somehow tap into it without exploding ourselves up. I try to, everything is you hear is CO2. And I try to basically get my students to understand the other analytes in our atmosphere, and methane being 20 times more powerful than CO2 when it comes to its impact in our environment. I actually told them you can see cows from the the satellites that can measure the methane released by cows, and they actually see that from satellites, which is kind of cool. But I think that's one of my biggest thoughts and concerns is increase of methane in our atmosphere and us not being able to bind it.
Yeah, you're absolutely right. I mean, we talk about CO2 a lot. Methane is molecule for molecule much more powerful greenhouse gas, although there's a lot less of it in the atmosphere than CO2.
At this point. Now, when you were talking about the permafrost and...
The other reason I think that climate scientists don't focus on it quite as much is its lifetime in the atmosphere is a lot less than carbon dioxide. Although part of what happens, as you know, methane when it breaks down is you get CO2 out of it.
Mm-hmm. And water.
Yeah, and so you degenerate from a very powerful greenhouse gas to a less powerful one, but it's still there. But the methane's lifetime, is around 10 years or so. But it is, there are certainly evidence that past abrupt climate changes like happened in the early part of the Eocene era, about 60 million years ago, might have been caused by a sudden release of methane.
So that was the tripping point.
Yeah.
The tipping point. Yeah, it just, it's a scary thought that in our global environment, there's so many factors that impact it. I had a discussion 2 years ago with a chemist, and I told him, go back and check your newspapers. The Earth did a 2% decrease in temperature when the planes were not getting into the air because of 9/11, okay? And I said, has anyone looked at the impact of water vapor up near the stratosphere? I mean, the highest parts of our troposphere, and its impact.
Yeah, there is quite a bit of research going on, and this current pandemic is another perturbation of the climate system. For a long time, there were hardly any cars on the road or airplanes in the sky, and so that's being, people are taking advantage of this experiment, if you will, to try to understand the system better. Yeah. We have a lot of work to do.
Is Washington really listening to you, the experts?
Not right now, not at all. And I hope that will change. But I'll tell you, my optimism comes from energy innovation going on in the East. I wish we were doing it, but as I said, I'm happy to buy power plants from South Korea because as a climate scientist, all I want is to solve the problem. If we don't, as a country, profit from that solution, that's too bad. I don't like that either, but it's too important to not do just because we're not manufacturing these things. We're already buying a lot of wind turbines from China and solar panels and Russia. And I think the innovation's happening there. It's just not happening here.
Oil has such a stronghold on our government. It's just, no one's going to listen. Not when you have the money and the power pushing it in a direction that we shouldn't be going, but we should be going towards innovation. Yeah,
I agree. Maybe we should go. I see that Mary has a question. Do you want to, if you don't mind, Alana, we'll just.
Mary's wonderful.
Okay.
Okay, am I unmuted?
Yes.
Oh, thank you. Thank you, Dr. Emanuel. How optimistic are you about the decrease in coal production and coal use worldwide?
Well, I'm optimistic about its decrease in developed countries like ours. Where I get pessimistic is when you think about places like India. 300 million people in India have no electricity.
Yeah.
Think about that. It's about the population of the US. No electricity. I was over in India at the end of the fall. You may have been there. It's staggering once you get outside these, relatively well-to-do neighborhoods. It's just staggering to see how people, and we hope that they lift themselves out of poverty, but we know that to do that, they're going to need cheap electricity.
Yeah.
They have a lot of very dirty coal in India that they could burn. And the temptation to do that is going to be very large unless somebody comes up with a clean and economical alternative for them to do that. They are going to build out solar and wind, and they should, but they can only do about 30 or 40%, and they're going to have to figure out something else to do in addition to that. So there's where I'm a little bit pessimistic, because the temptation to burn coal will be large. Of course, they're already suffocating on air pollution that comes mostly from these small cooking stoves that are being used all over the place. If they start burning coal on top of that, God, it'll be awful.
Not to mention, if you're saying it's dirty coal, you got all sorts of sulfur compounds going to be spewed in the air. And of course, they won't put the scrubbers on the stacks. And then you got your issue with acid rain. And of course, you got the monsoons. And that's going to thoroughly impact the respiratory systems of the people in the area.
Yeah. And then, you know, there's also Africa. There are large swaths of Africa where people live in poverty and don't have access to clean water, electricity. Where are they going to get their electricity? I'll tell you where I think they're going to get it from. They're going to get it from Russia and South Korea, and it's going to be in the form of nuclear energy, because they know how to build modern, safe nuclear power plants that are actually quite cost effective. Russia now is, you know, a booming nuclear export business. A lot of people don't know this. They're doing it fairly responsibly. That is, they're building these plants in places like Argentina, which is hardly an underdeveloped country, but they're building the plants there. They're supervising it. They're running the plants in some cases, but they're taking the waste back. That is, for them, it's a closed cycle. They're supplying the fuel and they're taking the waste back and dealing with it. And that's a very attractive proposition to countries that want cheap electricity built out quickly. And, you know, I think that's happened. South Korea has got a huge nuclear export industry. I was just in South Korea about 2 years ago, and it was just phenomenal what they're doing. And, you know, but I would like to see also the West participate, particularly because I think we can innovate the reactor designs faster and better.
How is China playing a role in this now? I know they have cut down on coal, but is it enough to make the difference?
Well, China is got all kinds of problems, one of which is that it's not a problem per se, it has a rapidly expanding economy with huge increases in energy demand. And they're playing all the games. They can't afford to choose and pick. They're developing everything, unfortunately, including coal. But they're developing nuclear very fast. They're developing solar and wind very fast. They're kind of built out on hydro. But they can't afford to say no to anything right at the moment. And the question is, where will it all go? Now, as you know, China has a terrible air pollution problem. I was over there last year and the summer in Nanjing and in Shanghai, and it's just basically you can't breathe there. And so they have a strong incentive, both from, well, mostly from a health standpoint, to get off of coal. But they have to balance that against this increased demand. That's a difficult game to play.
Dr. Emanuel?
Yes.
Just one more thing. Going along with nuclear, what do you think has been the major...
Oh, you just muted yourself, Mary, sorry.
One more thing. What do you think has been the major detriment to our country not going nuclear? 3 Mile Island was essentially nothing. Well, why did we not go nuclear?
You know, I think the problem is that one of the problems is the nuclear industry in the United States, is maybe worldwide, it's been terrible at marketing itself. I have a soft spot for people who can't market themselves. I don't think scientists are very good at it either. But, you know, they should never have called it nuclear. Nuclear is associated in people's minds with bombs.
It's horrible.
You meet a lot of people who think there's not much difference between the two.
It's true. And if you look at high school textbooks for the last 50 years, it's a chapter tucked at the end of the book.
And many of us don't teach it, unfortunately.
And unless you put it in, and you take away that stigma, it's really, because as you said, it's actually very efficient and it's very cost effective.
Well, I think we can learn something from a very interesting thing that happened in the medical profession. Some of you have probably had MRIs, I have. And when they were first introduced, they were called what they actually are physically, which is nuclear magnetic resonance imaging.
Yep.
I remember that.
They couldn't get patients to do it. They just wouldn't go anywhere near a machine. And it had nothing to do with radioactivity, by the way. It was just something that happened in the resonance in the nucleus. And nobody were scratching their head, and they just dropped the nuclear.
Yeah,
right?
exactly.
That's why it's an MRI, and then there was no problem.
Yeah.
We're up against.
We had to come up with a different term instead of nuclear energy.
We need to hire a professional marketer and take advantage of the fact there's new technology and use that to rename it. I know it sounds sort of ridiculous, but
I have faculty here, young faculty who haven't learned nuclear chemistry in their curriculum. So they don't teach it either. I am putting all the pressure I can on my faculty, but there is no time. It's the last chapter in the book, or as Mary said, somewhere tucked further down. I think the last time we have taught nuclear chemistry is when I taught Gen Chem.
Yeah, we've let the whole supply chain, including the chain of education and engineering talent, dry up in the U.S. And I think the chances of reviving that, in my opinion, are pretty small. I didn't say so in my talk, but at MIT, there's a lot of enthusiasm for fusion, because it's been a big technical breakthrough. And yeah.
At the tokamak, I was able to see one of those at MIT.
Yeah, and the breakthrough is in superconducting magnets. It's a materials breakthrough that allows you to do what they're doing in Europe for about a hundredth, 1% of the cost and 1% of the mass to build a functioning energy generating machine. And they're doing that now at MIT. And so there's huge enthusiasm. It's 10 to 15 year development, but for the first time in my career, I'm now kind of guardedly optimistic about fusion. Hope it happens.
Yeah, they had a big wheel, which was 2 stories high, that generated the power that the tokamak needed to get it started. And the professor told us that if it ever got loose, it would go right through MIT and keep on going. I went, wow. Yeah, I think we are restricted in terms of concepts and in terms of mapping what we have to cover in high school. There's just so much coming at us. We have to keep revising what we're doing. And I absolutely agree with Mary and others that we have to start integrating and rename.
Yeah, we do. I mean, it's a sad fact of life, but we have to be careful about terms and what they mean to people and how they're misinterpreted and so forth. Just have to be smart about it.
Marketing.
I know. It's a dirty word, and it should be. I mean, it's certainly in science, but you asked why did the nuclear industry fail? I think really a lot of it was bad marketing and bad press and Hollywood films and that sort of thing. So,
just as long as we don't build them through 3 major faults like Fukushima. I mean, my son lives in Nagoya with my 2 grandchildren, and I'm like, how could you build that many nuclear power plants so close to these major faults? I'm like, who was thinking on this one? And now they're unusable.
The American nuclear power industry had written many, many letters to TEPCO before that accident, warning that they should make their cooling independent of external power supply. And they just were ignored. So there was a big institutional failure. And the seismologists got it wrong too. I mean, they had estimated the largest quake they could have on the fault that ruptured was 8.3, and what they got was a 9. It's a logarithmic scale, so it was a very bad underestimate.
And a tsunami didn't help either.
No, that's what triggered the tsunami, of course.
I know, but it's like, wow.
Anyway, Folks, I'm going to have to pardon myself and excuse myself, but I've been really nice to talk to you all, and I hope I get to meet some of you in person someday.
Thank you very much, sir.
Thank you very much.
Thank you, Dr. Emanuel. Thank you very much.
Yeah. Take care. Bye-bye.
Okay.
Bye.
Bye.
It's great.
So if you'd like